Imagine you're standing in a massive, seemingly endless library. Your only job is to find one specific book hidden somewhere on these shelves. If you decided to just point at every single book and say, "That's not it," you would technically be correct almost every single time, but you would completely fail the actual task. This tabular dataset represents real-world credit card transactions. We have a massive volume of 99,900 legitimate purchases stacked against a microscopic fraction of just 100 fraudulent ones. If we train a standard classification model on this raw data, it returns a 99.9% accuracy score. In highly skewed datasets, that metric is misleading. A model can achieve near perfection simply by predicting that the rare event never happens at all, which validates a total failure to detect the fraud. This confusion matrix maps out our model's actual predictions against reality. It breaks down exactly where those 100,000 transactions ended up. Looking closely at the true positives quadrant, we see a hard 0. Out of 100 actual fraudulent transactions, the model caught none of them. Because normal transactions outnumber fraud 999 to 1, the algorithm optimized for the easiest mathematical path. It minimized its error rate by completely ignoring the minority class. To learn the boundaries of the rare cases, we have to force the model to see more of them during training. This 2D scatter plot shows our normal data points in a massive cluster and a distant, sparse cluster of just 3 rare target points. The obvious instinct is to fix the imbalance by duplicating those 3 points, but strict duplication forces the algorithm to overfit on identical records. It memorizes their exact coordinates without learning the broader patterns of what makes a transaction fraudulent. Instead, we use SMOTE, the synthetic minority oversampling technique. SMOTE draws lines between the existing rare points and spawns new synthetic data points along those paths. Generating plausible variations of the minority class allows the algorithm to map a functional decision boundary without overfitting to the original samples. Generating synthetic data comes with a strict rule. It can only be applied to your training set to prevent data leakage. The correct order of operations requires splitting the data first, isolating the test set, and then applying the resampling technique strictly to the training variables. Pause the video here. Using the variables on screen, write the specific Python code required to initialize SMOTE and verify the new counts. Proper code implementation forces the algorithm to treat the rare cases with equal mathematical priority during training. Here is the solution. We initialize SMOTE and call fit_resample on our training variables to balance the class counts. When we test a model trained on this newly balanced data, the results shift. The true positives rise significantly. The model catches the fraudulent targets. We made a deliberate trade-off. We sacrificed a tiny fraction of overall accuracy to vastly improve our recall. Prioritizing class balance ensures the model actually performs the detection task it was built for. When tackling highly skewed datasets, remember 3 rules. 1. Accuracy is a trap. 2. Evaluate with precision and recall. 3. Balance the data with SMOTE. Now that we have handled numerical discrepancies, we face a new problem: training a model when your data isn't made of numbers at all. We will tackle categorical encoding in the next lesson.